Okay, great. Thanks. So today we'll be talking about deploying optimized deep learning pipelines. So when I say that, I don't mean models. I mean everything. ETL, putting on a different hardware, even compiling, and optimizing graphs, and then bundling that into a binary using graalvm. Um, for those hoping for like a graalvm tutorial, move that to the hallway track. This will mainly be focused on, I think, a lot of the prerequisite topics because this is a fairly new thing that people are seeing. And the use cases, a lot of people aren't exposed to it uh, quite as much because they either don't need to because they already have big servers, or there's very specific use cases where this stuff is required. So just as a caveat for those attending the talk today. Um, so getting right into it. So I'm an O'Reilly author. I've been maintaining the Eclipse Deep Learning for J framework since 2014. So I've been at this a long time. If you want to reach out, my handle is the same on Twitter, GitHub, and LinkedIn. And I'm at SkyMind along with my colleague Eduardo, who spoke earlier at Express AI. So if you have any questions, also feel free to jump over to the Express AI booth for more. So things we build that you can download today: Deep Learning for J, conduit serving, Java CPP. So heavily, there's a big focus on kind of the JVM stack. That's where I've been for a long time now. We kind of started as kind of the place to build and deploy ML models. That's kind of still what we're doing. That's what we're doing today. But we've expanded a bit. Trying to focus heavily on making faster applications running from the JVM, but otherwise, you can use stuff from Python. So we're behind quite a few of the, like Java CPP. If you're not familiar, is actually, the baseline packaging for a lot of famous libraries. TensorFlow Java, I think, being the biggest one, but also more recently, Java CV, like OpenCV, FFmpeg, among others. So we kind of use it as like the Python ecosystem. How everything interrupts via NumPy arrays. We do the same via Java CPP's pointers. So if you ever look at a Java CPP project, it's like programming in C++ because there's pointers, memory free, and allocation, and all that. So we use a lot of those little primitives and use that to deliver optimized math code plus applications for production. It's kind of the core theme here. So that could include serving models, packaging end-to-end applications, or even just running very fast numerical code or HPC code on, in a Spark environment. There's a lot of different use cases there. If you have any questions, reach out at hello@conduit.ai. So breakdown, the problem scope. So in just, sorry, an overview of the presentation, there's, kind of problem scope, trends. This will be a heavy focus on ML, the general area of ML ops. So I'll say what we are and what we aren't. For those that maybe not, aren't familiar with the space, I'll give like a brief introduction to what I'll call DL ops. So focus on deploying and running fast and large neural networks on different kinds of coprocessors, among other things. ML pipeline components. So, clarifying that, you have a model and then you have other stuff. What is it? Performance workload trade-offs. So if you're into understanding the whole ML stack, all the way down to HTTP versus gRPC versus, your own custom binary protocol, stick around. Tools and techniques for optimization. So if you want to apply some of the stuff like deep learning compilers and some of these other things, I'll also give some tools there. And then I'll give a concrete overview of kind of our opinion on what all this stuff is as briefly as I can. So problem definition. So some acknowledgements for those that are like a little bit worried about hype. I always try to focus on pragmatism in my talks. Most people aren't deploying deep learning models. Most people just use XGBoost or Random Forest and they're good to go. They don't need all this stuff. So if you want to stick around, if you do have, if you do need this stuff, then great. If I haven't hit your use case in this talk, I would be really curious to hear more. Your company probably doesn't have Google, Facebook, or GPT-3 size problems. You probably just have, analytics. That's okay. And people will deploy tens or hundreds of analytics models and drive a lot more value than one neural network might. So just keep that in mind. Accuracy, data quality, and bias are critical to the success of a model just as much as kind of the performance stuff I'm talking about in this talk. And finally, the tools and techniques in this talk are mainly for inference. not training, or at most up training a model. So like fine tuning it or adding additional data to the model, and not for training a model from scratch. There's a lot of material on that, because that's where you have to start, is training a model. But around inference, when generally people just throw up a server with HTTP and they're done. Some use cases require more than that though. So what do you do when costs get out of control, or you need to deploy a model to a mobile device? What are some of the things you can do? Those are the kinds of areas we'll be focusing on here. So there are broader categories, labeling and data quality, setting up a REST API, packaging, like how do you deploy an ML pipeline, and experiment tracking, which weights and biases does. I think they're kind of and I guess ML flow as well are kind of the standards in this space. So if you use those tools, we're not that. We're kind of like a lower level component of that you might consume from something like those tools. So why optimize? Intro to DL ops. So the main situations where people need this stuff are either transformers, NLP, or mobile devices. Most of the time, whenever we have a phone and we want to run a model, you want to run it locally because of privacy issues or what have you. That's gonna fall into the bucket of vision or speech generally, with 90% of it being vision. Taking a picture of some clothes and then seeing what the price is, or taking a picture and and then decide for better ad serving, or all sorts of things that the big ad tech giants are kind of doing. Or there's just like basic security, who's at my door, and I want to run that on a small like Jetson Nano or Raspberry Pi. These things are getting smaller and smaller, and the more the cheaper we can make computer vision deployment, the more it'll be used, for better or for worse. So I think more people, if they're thinking about this, might be just more familiar with the standard bird architecture or anything transformers related. That's probably where you might be more familiar with some of these things, or bigger language models. That's where you might need, the trillion parameter models you hear about are the ones where you might start asking, well, how do we actually run this ourselves? So some of these techniques will either help you reduce your costs when running these models, or just in general, maybe be able to run, help you run and train some of these models on something that isn't $1 million cluster. So problem size. So computer vision need to be compact to run on mobile or at the edge. NLP models are increasing in size. We see GPT-3, we see BERT. Every like big tech company right now is actually competing for, I built the 4 trillion parameter neural network, I'm going to build GPT-7. There's a lot of that going on right now, and you have Hugging Face directly monetizing this, saying, hey, we'll help you deploy those. We're just going to charge you for it, but we make it easy to do. We'll give away the ability to do it. That's kind of their thing. So there's still a lot of questions around how do we shrink models. That's kind of the question I'm interested in. How do we reduce compute cost? A lot of players in the space don't really have a vested interest in making these models smaller, because they want to they want to be able to say, we can provide you amazing services using our own technology. Don't worry about running it. We'll just use it ourselves. We'll give it away, but there's a whole there's a big gap between academia and industry research labs because of that. Because of the resources required. So anything, and I think any direction in this space is welcome. So anyone applying these techniques more widely is highly encouraged. So one of the big things you run into is RAM. GPU RAM is not very big. I think we're starting to see like 24 gig GPUs, but are still super expensive. Generally, most laptops, that are just even the things you see free on Colab are like maybe 6 gigs of RAM, 8 gigs of RAM. If you have like a decent, you're still paying for that though. Like my laptop has an 8 gig, like a 2080 in it. It's not a 3080, but I haven't needed anything else. That's only 8 gigs of RAM. So you either end up using multiple GPUs, or like what my colleague talked about, Eduardo talked about, like the Aurora card, which is cheaper, faster than a CPU, but has a lot more RAM. And there's other players in the space like Cerberus Systems, who built the biggest, I think like the quote unquote the biggest coprocessor in existence right now. You have GraphCore doing these kinds of things. So they're with their IPU. There's different alternatives. They all have their own trade-offs of execution speed. Neural networks are good at RAM, etc. The cost. So in summary, these things are expensive. And running these things in production can be even more expensive. So some people try to minimize, either make it run on CPU. That's what most people do, and say that's fast enough. Or if it's like if performance is real-time performance is mandatory, then you need to set up all sorts of tooling around being able to run a coprocessor like a GPU in a data center. So components of an ML pipeline. So what are the components? So generally it's two parts: your actual model and your input preprocessing. So what people don't think about is actually optimizing the full pipeline from data collection, vectorization, converting it to a matrix or a tensor, and then actually putting it into a model. That kind of aggregation for recommendation engines, big different kinds of systems, maybe something where Kafka's involved, or whatever buzzword you have of the week for your streaming platform, your database. You need to be able to collect that data, aggregate it effectively, and then convert it to a vector, and then put it in the model. That part, where the tooling is attempting to solve that, but I still don't feel like has solved it effectively. I feel like there's still a lot of room to make that process easier, especially when you're pre-processing different kinds of data. NLP, for example, has the tooling around converting text, which could be a sequence, or just your standard bag of words, to a vector varies widely, and the form it needs to be in might be varying length. So you need masking and all these other things. So you need a weird mix of domain knowledge and then knowing what kind of tensor and shape to convert it to actually put it into a model. That whole workflow is kind of, I think, what Hugging Face has made easier. But just knowing how that works, there's ways to optimize that as well for people. So just when I say pipeline, I mean everything, not just the model that you're thinking of. So a bit of a primer. So I already kind of mentioned it. Raw data needs to be converted to arrays. Could be pandas, could be whatever you can think of. Could be an SQL table. Data can come from anywhere. There's a wide variety of protocols nowadays for streaming, just a standard web, or your SQL database. Data can have different formats. In memory, you have Arrow now, which I think has helped the ecosystem move forward as far as taking a pandas array, directly converting it to without copying the data or anything into something that Spark understands, or Flink, or what have you. So these things are getting better. The fact that like the formats exist where two things can talk to each other and say, hey, we're the same, there's no copy needed, is beyond the the network copy or what's necessary to run it locally, or just run the compute where it needs to. That's really nice. So if we can reduce that overhead, great. Data scientists probably are familiar with gRPC, but it's used everywhere. Kubernetes being a big driver of that. So gRPC allows you to generate your services, your service definitions, and then you can make two things talk to each other. gRPC itself can speak different protocols as well, so it kind of gets a little convoluted. But in general, there's lots of ways to move data, consolidate it, and then make a model score whatever it is your raw input is. So data movement and storage is its own set of problems. It is generally a prerequisite. You need to get that right before you kind of get into even the ML part. So if we think about the broader topic I'm mentioning here, this is kind of like 3 tiers down. You have like just storage, then you have moving the data around, then you have the vectorization part, and then you have just normal ML models which people use, and then you have the very specific thing that we're doing with trying to make optimized models run. So you can kind of see like how deep down the funnel this really is. So models, for those that aren't familiar, maybe for an engineer, you don't really know what how a model is stored. It's used using HDF5, protobuf, or pickle, depending on the various frameworks you use. These models are big. They contain like generally a DAG, just like this. An add is like X plus Y, output Z, and then that's all connected via a computation graph. There's that configuration plus the actual matrices themselves, which can be very big. So models don't have to be all like, not every model is 10 terabytes big or something, but it's not uncommon to see 500 megabytes, 250 megabytes, 2 gigs. Those are not that rare. You see those quite a bit. So again, just knowing how to store that with your ETL pipeline, versioning all that, generally people just say, well, just put it into a Docker container. It's what a lot of people do. that has its own trade-offs as well. That's what I think that's what you're kind of forced to do today, especially since a lot of this code runs in Python. There's still really there's like some good ways to package Python code, but it's still very sparse. And Python as a server runtime, not, a lot of people running alternative runtimes for this stuff. So what do you do in that case? So there's a lot of questions just around, what do you do with a model file? Where do you put it? How do you hook it up to a model runtime? What's, there's a lot of code out there now that makes just focusing on these file formats easier. We have an opinion on this as well, of course, but there's alternatives like Microsoft Sonic's runtime. TensorFlow kind of did this with TensorFlow serving. Like, we just have something that's like C++ with gRPC that knows how to load a TensorFlow model and execute it. So I kind of view models as a, one runtime may train it, another may use it. So that split paradigm has been around for quite a while, because a lot of this underlying code is C++ anyways, or Java, or something aesthetically typed that's easier to deploy. So what you do with the model file is up to you. How you interact with it will vary, but hopefully that makes sense. So putting them together, ML pipelines are not just models. ETL varies. It can be JSON. It can be a mix of things, or even within, it can be within the model. tf.data is an example of that, like kind of trying to extend that paradigm. And then you have your metrics and experiments. So model tracking platforms try to do all this at once. They generally have a very simple version of it, and that generally will work for a lot of people, especially when you're just doing a proof of concept. And in a lot of something that you kind of takes a while to learn if you're in a software engineering bubble is most models don't actually need a software engineering team. Most the data scientists themselves are kind of the consumers of these models. So just the bare bones things that experiment tracking platforms give is probably good enough. So the tools need to do better bringing this stuff to and exposing it to where the users are running the experiments. So some of the key performance considerations: better data interchange, faster protocols in HTTP, better memory file formats for data interchange. That's where something like Arrow comes in. Better storage. You need data stored in SSDs generally. I mean, not everything. It depends on your frequency. It depends on the use case. Like a data lake, for example, will be your standard. This is where all the analytics happen. This is where we aggregate all of our data. Your data warehouse, where this is like the real canonical production store, and that has regulations attached to it, among other things. And then your pre-queue. One thing when interacting with any sort of coprocessor, make sure that whenever you're storing your data, make sure that it's easily, you can just send it all at once, in big batches, not small batches, to the coprocessor, like the GPU, the TPU, because otherwise, typically latency hiding will be a big problem. What I mean by that is the overhead of sending data can overcome the benefit of the faster processor. In that case, you need to make sure that your data movement doesn't kind of outpace your, or be the bottleneck for your compute. Faster models. So something people don't typically think about is when they call model.save in Keras or what have you, what can we do to optimize it? Well, it turns out, precision's a big one. Your data type, the smaller your number is, the less time it takes to compute something. GPUs, have this like mixed, you've probably heard the buzzwords like mixed precision, half, FP16 half. Those are just basically numbers that are smaller. Like long versus int, doubles versus float, and kind of extending that out further. So if we can, force models to be, you only use certain data types, especially for inference, as long as they produce something like the same result, then if it's faster, then there's no downside to that. A data layout, so it turns out CPU is faster with NCHW, which means, number channels, like if an image is RGB, right? So you have 3 channels. So you have number, channel, height, width, like the height and width of the image. GPUs are, channels last, as it's called, in HWC. So there's like various reasons for this, but just in general, just understand that, the way you input your data matters, the way you save your model matters, and what's in the model matters. Like the way you write it's just like when you write a bunch of redundant code that's not needed for training, and you just put it in your model, that stuff can be pruned. So there's a lot of techniques around, even just how you program these models nowadays. So as I mentioned, removing redundancy. So some execution platforms will try to say, okay, what's the bare minimum? What's the minimum spanning tree of the operations I need to run? in order to get to the necessary result. If you can have less parameters, the better. And again, format, you may need to export to different formats to run on different platforms, like TorchScript, normal PyTorch, TF-Lite versus TensorFlow. There's all sorts of various reasons that these TensorFlow versus TensorFlow Lite exist, for example. It's just because it's a different use case. And the problem is that people don't think about is the supported operations will typically be different. Or the way they implement that support for a particular op can matter. For example, like the way you might implement, say, a TensorFlow op in Onyx might be combining a bunch of Onyx ops together to approximate the result from TensorFlow. It could. Sorry, my headphones were muted there. Sorry, we're good to go. I just like had to charge them. So anyways, so yeah, so the way, so again, support will vary. So just be aware that when you try like converting all these framework, all these things together, so just converting model converters are a problem. So tools and techniques, quantization is one thing. Knowledge distillation, kind of a teacher-student model. Train a smaller model on the output of a larger one to approximate the same result. Batch norm folding. So batch norm, for those that aren't familiar, is just a way of saying, what's the running mean standard deviation of the mini batches. Normalize, in the middle of the graph, just normalize the kind of the output, which kind of keeps it from diverging. Is kind of the core idea. That's kind of slow. It has its own overhead. There's what you can do is you can actually kind of bake in the mean, and you can take that mean standard deviation and just bake it into the previous layer. So that allows you to like remove some extra redundancy from your models, and connected layers decomposition. So okay. So optimizing data. Sorry, I'm gonna hurry a bit since I'm gonna be out of time soon. So optimizing data format, change to a more efficient binary format, pre-convert your data to something like Parquet or NumPy arrays, remove layers, and minimize communication overhead, which we kind of already covered earlier. So some tools to be super concrete. There's there's a lot of, so Grappler from TensorFlow is one for optimizing TensorFlow models. There's Simplify for Onyx, which just removes a bunch of the redundant ops and things like that. So those are graph optimization. And then there's the deep learning compilers. That's its own whole category. So TVM is kind of the main one in this space, but there's also Glow from Facebook and MLIR from Google. And what they do is they handle the graph, they handle the graph computation. They actually like run kind of a search, parameter search to identify the optimal configuration for a given piece of hardware for a given graph. These searches can take 12 hours to 2 days to run sometimes. So what I would say is, if you're going to look into deep learning compilers, look for simple wins first. Just changing the graph structure, for example, versus like trying to do a full like end-to-end search. So if anyone wants to know more about deep learning compilers and all that, I've played with quite a few of them. If you want to know anything in particular, but yeah, in general, just be aware that while this is a new space, it will be important in the next couple of years. TensorRT optimization. So, one thing I would say is, if a vendor provides an optimizer, try to use that, because they could, one thing TensorRT does is it will say, oh, you have a convolution operation here. Let me replace this with the cuDNN equivalent. It does like stuff like that. So again, it swaps the result, the ops that are executed in order to, that are vendor specific, in order for them to be faster. And then for the fast AI framework, there's also faster AI, which kind of consolidates these techniques into fairly easy to use format. So now finally the graalvm part, for those that are kind of curious what an end-to-end application might look like of this. So first of all, why graalvm? It's capable of allowing existing JVM code bases to have faster startup times. That's kind of like the main use case that people pitch. There's also just the single binary use case, like, hey, I can ship a single binary. I don't need a Java runtime. That's always kind of nice. We tried to solve that with JLink, but there's always trade-offs to that. So if we can do that, with completely native optimized code, that that allowed us to kind of wedge in like other languages like Ruby, JavaScript, You can do all sorts of like weird multi-language interop, and the cross-language support is getting better. We mainly use it for packaging, but combine with other things, but it does have its advantages. We use Java CPP for all the libraries you can think of in Python. We take those. We have Java bindings for all of them, because what Java CPP does is it actually allows you to kind of declare a way to generate the JNI code for actually talking to C++. So we just run it as a Maven plugin, and it's great. It's easy, and I haven't had to write manual JNI code in years. We just use this, and it's worked for a long time now. And that allows it, and coupled with that is the ability again to, pass around native pointers into pointer addresses, and that allows us to get, very, very like a very performant code, despite using the JVM. And then, obviously we have, when we're kind of like just debugging these workflows, we can just, debug in Java with its great tooling. This is kind of an overview of our opinion of this. So what do you got in here? You have YAML for the configuration. Yes, yeah, more YAML, but it works. Then there's the models. So you have a model file. You have a model, you have a pipeline configuration. So again, a pipeline is what I described before. It's the pre-processing, even the post-processing, like how you return the result to the user can matter. Like, for example, if you just want to return an end user a softmax array, that's probably not what they want. They probably don't know that, each, the max of the column on each row is, the selected class. They may not know that. So you need to give it to them in a form that they can take, like cat or dog. Then they can use it themselves. So that whole pipeline plus a model file, generally take that to our tooling. We have our own opinion on this. Our same diff framework in DL4J is again kind of our opinion on running math code. We can actually import all these models generally, and then we use it for our own internal use cases for packaging, training models. Deploying on Android. There's a lot of various use cases, and then as well as just our own production systems. We have, and then use graalvm, like the combo of our same diff runtime, graalvm, and byte, our in Java CPP to create like one binary. So one cool thing here that's not that I kind of have to elaborate on is, in our same diff runtime, we actually have the ability to say, given a model pipeline, we'll look at the graph and create a custom binary for just the supported data types you need, and just the ops you need. That allows you to reduce binary size, and this all just gets baked for free into the binary. You never see this. So if any of that's interesting, please do let me know. And then again, you can run on different chips, like your standard, your ARM GPU, your ARM, your NVIDIA, your Intel CPUs, and of course the Aurora chip. And then how do you use it? Well, same thing. You have your configuration YAML. We have a Python SDK, and then your model file. And so what we do is we actually have a Python SDK that's linked against the specific binary produced by this process. And then all you do is you just you load a training config, and then you pass in NumPy arrays, and then it's all zero copy. There's no overhead. We directly can look at a NumPy pointer and say in memory and say, oh, we know what this is, and then convert it to our equivalent, and then run all the execution, and then return it as a NumPy array. So it's a really nice way to run end-to-end pipelines and package them as a single binary. And it's all AOT thanks to graalvm. In this case, in our workflow, we produce a shared binary or shared library with the necessary components all in there. So what's crazy is, in practice, it's generally a 500 megabyte to 1 gig binary, which actually isn't bad. I mean, compared to what you might see in the Python world. Generally what we do is we just produce binaries for the platform we want to run, the platform and model we want to run on. All configurable from all runnable from Python. We have JSON YAML for just running the model config, and then we have a Python wheel for each platform for actually integrating with everything. That's kind of, again, our opinion on how to consume all this tooling. So at the various levels, you kind of have the, what you might do here is you might, at this step, you might do any sort of like model optimization before you package a model. You might look at, then after the optimization, you might look at the data types and whatever's present in there, and then compile a binary just for that, as well as the associated libraries. That's when I think of end-to-end, that's literally end-to-end. And that's kind of the goal of a lot of what we focus on building day to day. And then again, just all consumable from Python just via standard Python SDK. So for those that want benchmarks, just on average, a lot of this stuff is still kind of early yet, but in our years of experience, we found that, we're still linking against the same C code that Python is. So we're generally faster, just because of the, just because of Python versus Java as far as speed goes. So for real production applications, the major thing to think about is just, your standard memory allocation and all those other things in production. But beyond that, we execute the same math code everybody else does. So since we have our own library, we use all the same optimized libraries people do, like cuDNN, et cetera. So in practice, we haven't found many, if any, performance differences, or in general, like we've been faster. If people have specifics, I'm happy to talk about it in the hallway track. But otherwise, that's kind of those are kind of, I think, the core ideas I wanted to communicate. So I will leave everything open for either questions or hallway track. Thanks for your time.